Hello, welcome to the second part of physics. And right away, we're going to start this course with a study on oscillatory motion. Now, what is oscillation? Oscillate. Doesn't it mean moving back and forth? Have you seen oscillating objects around us? In fact, there are many examples of objects oscillating around us. Now, let me show you one example right away. Have a look at it carefully. You may find it difficult to see it well because of the shadow. Now, here I have a loaded spring. What is a loaded spring? Now, that's the load, and that's the spring. If I suspend this load, now, this is called the equilibrium position of the load. Now, what happens if I pull it down to a lower extreme? Now, those who do it will know that when you do it, the spring will actually pull you back. So, you can see the load oscillates between a lower extreme and an upper extreme. That is an oscillatory motion. Alright, let's put that away and look at that in a demonstration. Okay. If a loaded spring is pulled down and released, the system moves up and down about its equilibrium position. There you are. It moves up and down about its equilibrium position. The equilibrium position is the rest position. And it will be somewhere there, is that right? Okay, now this up and down motion of a load is actually called an oscillatory motion, an oscillation. When the load is pulled down to the lower extreme, when you pull down the load to a lower extreme, you do work, don't you? Yes, you actually do work to pull it down to the lower extreme, and that work will supply potential energy to the spring. Is that right? And when you leave it, what happens to that potential energy? Well, that potential energy is going to give that mass some speed, and the object is going to speed up towards the equilibrium position. And when it reaches the equilibrium position, it has maximum speed. And therefore, can it stop there? No, it is going to go up, compressing the spring, giving the spring again potential energy. So, let's now look at the energy conversions of the spring as this process happens. So, the kinetic energy at the equilibrium position does work compressing the spring so that it moves to the upper extreme. Is that right? There you are. So the spring will now move between the lower extreme and the upper extreme. The compressed spring has potential energy, and it does work pushing the load back to the equilibrium position, where it will have kinetic energy. So the spring has potential energy at which positions? It has potential energy, it has maximum potential energy at the lower extreme and also at the upper extreme. And how about in between? Well, in between, it has both potential and kinetic energies. So, it has maximum potential energy at the lower extreme, maximum potential energy at the upper extreme, and all the energy is kinetic at the equilibrium position. And in between, it has energy that is a combination of the potential and the kinetic. So let's map that now. At the equilibrium position, the potential energy of the spring is 0. So here, all its energy is kinetic. It has no potential energy. The spring is not stretched at that position. Only a stretched spring or a compressed spring has potential energy. So the potential energy of the spring is 0 at the equilibrium position, and its kinetic energy is maximum. Whereas at the upper extreme, when it moves to the upper extreme, the spring gets compressed. All the kinetic energy is now become potential energy. Kinetic energy is 0, potential energy is maximum. Similarly, at the lower extreme, kinetic energy is 0, potential energy is maximum. So I want you to be familiar with these energy conversions as the oscillations continue. Now, the amount of stretch of the spring from its equilibrium position is called the displacement y of the load. You see, this is the equilibrium position. The load is going to move up. That means it is going to move from the equilibrium position a distance equal to y. And what will happen to that y? The y will keep changing. Where will y have the maximum value? You can see y will be 0 at the equilibrium position. Its value increases to a maximum value at the upper extreme. What is that maximum value? We're going to talk about that. So this is what we call the displacement, and we will call it y. And what is the maximum value of that y? This is the maximum value of that y from the equilibrium position to the upper extreme. And we call that the amplitude of oscillation. So what is the amplitude of oscillation? Amplitude of oscillation is the maximum displacement of oscillation. Alright, and we will use A to represent the amplitude. So, you can now tell me, how does the displacement y change with time? You can see y equal to 0 here. It increases to A, then it will decrease to 0. It will then decrease to a lower extreme. I'm going to call it negative A as I go on. So as the load oscillates between two extremes, its displacement y changes, reaching a maximum value A at the upper extreme and a minimum value negative A at the lower extreme. That means the value of y will oscillate between negative A at the lower extreme and positive A at the upper extreme, and that will continue. We are now going to obtain an equation for the displacement y as a function of time. Now, those who understand trigonometric functions have a clear idea now how y changes. You see, y increases to a maximum value, decreases to 0, then decreases to a negative minimum, increases to 0. Are you familiar with that kind of a variation? What function in mathematics represents that change? Now let me show you a couple of examples of oscillation before we move on. Now let's see if I can get that website opening up. Now, if you look at the oscillation of the loaded spring, and you see on the right side how the value of y changes. How does the value of y change? Y is 0 at the equilibrium, maximum 0, minimum 0, and it keeps changing like that. Now, there is another kind of oscillation on the right side. We are not going to be concerned much about that. We will be looking at this oscillation and how the value of y changes. Alright, have you got any idea what mathematical function will represent how that y changes with time? Okay, we will look at that in detail as we go on. Now, let's now look at an example which we are going to use to construct a model. Now, I want you to look at this model I have constructed. this is like a bicycle pedal. Now, most of you are familiar with that, is that right? If you now allow this to go in a circle, that means you're applying force so that the pedal goes in a circle like that. Now, watch how the shadow of the pedal, the position of the shadow changes. You can see that's the shadow there. Now, this is the equilibrium position. Look at the position of the shadow. Now, as the pedal moves up, the shadow also moves up. It reaches the maximum position there, and thereafter it goes down, back to equilibrium, and now look at the way it's going to go. It's going to go to a lower extreme and back to the equilibrium. So, as the pedal goes round in a circle, the shadow of that pedal moves up and down. Isn't it similar to the oscillations of a loaded spring? That's correct. Now, let's consider an object moving around a circle of radius A. In other words, this is the object that is moving in a circle of radius A. That's the radius. The object is moving in a circle like this. And what happens to its shadow? Its shadow simply moves up and down. Okay, let's say that's the radius of the circle, and the radius is A. At t equal to 0, now in physics, whenever we start something, well, that's when we start our clock. At t equal to 0, the object is here, and we call that position P. Now, a little while later, the object comes to the position Q. You see? Now, this is the position P. A little while later, the object is at Q. That means the radius has now rotated through an angle theta. So that's the angle theta. Okay. BC is the diameter of the circle. And what I want to do is draw a perpendicular from Q to that BC. A perpendicular drawn from Q to BC touches the perpendicular at O. And now, can you construct visually in your mind what will happen to this point O as the object continues to move in the circle? Now, is it similar to the shadow of the pedal? Well, I think so. Well, O is called the projection of the object that is moving along the circle. As the position of the object on the circle changes, the position of its projection will also change. Now, if the center of the circle is the origin, suppose this is the origin, then when the object is at P, the projection is at 0. Is that right? If origin is 0, when the object is at P, the projection will be at the origin, which corresponds to 0. When the object is at Q, where is O? O is here. And that's where O is. Now tell me, now why is the distance that the projection has moved from 0 to the new position O? Now, that is the displacement of the object in oscillation. Is that right? And now, how does the value of this y change as the object on the circle keeps moving? Let's look at that in the next slide. When the object is at B, anybody tell me, when the object is at B, where is the projection O? Well, as the object continues to move towards B, O will continue to climb towards B. When the object is at B, the projection is also at B. Can you understand that? Alright. Now, what is the value of y now? The value of y now equal to the radius of the circle, which is A. That means the value of y has become the maximum value now. Now, what is the value of theta at this time? What is the value of theta when the object is at B? Now, when the object is at B, the radius has rotated through 90 degrees, or we call it pi by 2. Is that right? So, when the object is at B, the value of theta is pi by 2. When theta increases, look at this, when theta increases from 0 to pi by 2, the value of y increases from 0 to a. Now tell me, what happens to y as theta further increases to the second quadrant? What happens as theta increases from pi by 2 to pi? What will happen? That means the object is now moving from B and continues to move. What will happen to O? O will come down. It means y will decrease. Is that right? That's right. So, as theta increases to pi, y decreases to 0. So as theta increases to pi, the value of y is a here. It will decrease from a to 0 gradually. And now, as theta increases from pi to 3 pi by 2, can you picture what happens then? O is going to move down. That means the value of y is going to decrease from 0 to negative a. And when the angle increases from 3 pi by 2 to 2 pi, the value of y is going to increase from negative a to 0. So watch that one more time here. As the angle increases from 0 to pi by 2, y increases from 0 to a. And as the angle increases from pi by 2 to pi, y decreases to 0. And the angle increases from pi to 3 pi by 2. The value of y decreases to negative a. And the angle increases from 3 pi by 2 to 2 pi. The value of y increases from negative a to 0. So for one complete rotation of the object on the circle, the value of y, the displacement of oscillation, increases from 0 to a, decreases to 0, decreases to negative a, and increases back to 0. You can see how beautiful oscillation. You see, oscillation is constantly changing back and forth. Okay. Now, the displacement y is actually a function of theta. What does that mean? It means the value of y depends on the value of theta. And the motion of O is the projection, is actually similar to the motion of the loaded spring. Do you agree with me? I think so. Alright, let the center of the circle be M. That's the center. And we are now going to obtain a mathematical equation for y. Okay, so watch this carefully. We have a right triangle MQO where, watch this now, MQO where MO equal to y is the opposite side to this angle. Anybody tell me what is that angle? This angle is the same as theta. Can you figure out why? They are alternate angles. So that angle is theta. So we have a right triangle MQO where this angle is theta. The side opposite to that angle is y, the displacement. Tell me, what does the side MQ represent? Any familiarity with that? MQ is the radius of the circle, which is A. Okay, so in the right triangle, what is sine of angle theta? You're familiar with your trigonometry. Sine theta is opposite side divided by hypotenuse. It will be y divided by A. MQ is A. And that gives me, if you notice, if I multiply both sides by A, what happens? I get y equal to a sine theta. You see how beautifully we got an expression for the displacement y as a function of the angle theta. Y equal to a sine theta. And if you know the graph of sine of an angle, you know it looks like this. This is the graph of sine theta. You see? As theta, when theta is 0, y is 0. When theta is 90 degrees, our y is maximum, equal to a. When theta is 180 degrees, displacement is 0. When theta is 270 degrees, the displacement is negative a. And when theta is 2 pi or 360 degrees, the displacement is 0. You can see how the displacement changes. We say the displacement is a sine function. Is that right? Yes. So the displacement is now represented by y equal to a sine theta. Okay. Now, we want to represent the displacement as a function of time rather than as a function of theta. Is it possible to write this equation y as a function of time? Well, I think if you go back and recall definition of angular velocity. Anybody remembers the definition of angular velocity? Angular velocity is the rate at which the angle is being described. In other words, omega. We represent angular velocity by omega. Omega equal to theta over t, the rate at which the angle is being described. What is the angle described in unit time? Is that right? That is angular velocity. So omega is the angular velocity, which is theta over t. Tell me what is therefore theta equal to? If omega equal to theta over t, what is theta equal to? Multiply both sides by t. We get theta equal to omega t. Alright, let's take theta equal to omega t in that equation. What does the equation now become? The equation now becomes y equal to a sine omega t. Watch that, that omega t is a single quantity. Alright, now we obtained the displacement of oscillation. You see, y stands for the displacement of the oscillation as a function of time. Y equal to a sine omega t. And don't forget that, that's a very important equation. And omega is actually called the angular frequency of the oscillation. And we will talk about this a lot, and you need to remember the identity of that quantity. When omega is a constant, the value of y depends only on time, because A, the amplitude is a constant. That's the maximum displacement. Omega is a constant. Is that right? So, when omega is a constant, the displacement y depends only on time t. Okay. The vertical oscillations of a load attached to a spring is actually similar to the vertical motion of the projection of O. In other words, the projection O moves up and down in a way exactly similar to the motion of the loaded spring. And the displacement of the oscillation is given by y equal to a sine omega t. Let's draw a graph of that. Now y equal to a sine omega t, that's the origin. How does the graph go? The graph is a sine graph. At t equal to 0, the object is, well, the displacement is 0. And as time increases, the displacement increases to a maximum. It comes to 0. It decreases to a minimum and increases to 0. That's a sine graph. Now here, A is the amplitude of oscillation. What does amplitude stand for? Amplitude is the maximum displacement. And there is the amplitude. That's the amplitude of oscillation. Now here we assume that when t equal to 0, the oscillating object is at the equilibrium position. You see, the identity of the equation can change depending on the time we start looking at the oscillating object. I want you to look at this carefully. Now, in this example, we said that when t equal to 0, the object is at the equilibrium position. And that's what this represents. On the other hand, if you start your clock when the object is at the upper extreme, well, the equation will slightly change there. What kind of change will there be? Anybody suggest to me? Suppose we say when we started our clock, the object was at the upper position. All right. Now, if at t equal to 0, the object is at B, that is here, that means the position corresponds to theta equal to pi by 2. That means when we started the clock, the angle has already become pi by 2. And therefore, how will you represent the function now? The equation now becomes y equal to a sine omega t plus pi by 2. Why? Because when we started the clock, you see, we forgot to start the clock here. We started the clock when the object is there. That means the radius has rotated through an angle pi by 2. Therefore, you've got to say the equation of y now is y equal to a sine omega t plus pi by 2. That means when this t equal to 0, now the object is at B. Well, when t equal to 0, if the object is at the origin, the equation will be y equal to a sine omega t. But now, we started the clock when the object is at B. So, the equation now is y equal to a sine omega t plus pi by 2. If you know your trigonometry, anybody here knows your trigonometry well enough to tell me the expansion of sine omega t plus pi by 2? Do you want me to show that to you? Let me see if I can show that to you. Well, you know that sine of a plus b is sine a cos b plus cos a sine b. So what is sine of omega t plus pi by 2? Will be sine omega t cos pi by 2 plus cos omega t sine pi by 2. You see that? Now, as a result, when you come here, what is cos of pi by 2? I don't think many of you remember. Cos of pi by 2 is 0. That means this term will disappear, and therefore sine of omega t plus pi by 2 is cos omega t sine pi by 2. Now, what is sine of pi by 2? Sine of pi by 2 is 1. So, this simply becomes cos omega t. Isn't that beautiful? You see? So, sine omega t plus pi by 2 is the same as cos omega t. Therefore, that equation now becomes, I can write it as a sine omega t plus pi by 2 become cos omega t. That means if I now draw the graph, how does it look? Look at that now. This is the graph of a cos omega t. So at t equal to 0, if we started at the origin, this is how y will change. Y equal to a sine omega t. On the other hand, if we started the clock when the object is at B, that is how y will change. And actually you can now work out many different combinations of the function depending on when exactly we started the clock. Now the angle pi by 2 is called the phase angle of oscillation. So what does the phase angle tell you? The phase angle is an indication of the initial condition. Where was the oscillating object when you started the clock? What will be the phase angle for this oscillation? We started the clock when the object is at the origin. The phase angle will be 0. What is the phase angle for this oscillation? You started the clock when the object is at B. The phase angle is pi by 2. Alright, for convenience, we will represent the phase angle by the Greek letter delta. So, what will then be the equation for oscillation? The displacement of an oscillation can now be written as y equal to a sine omega t plus delta. You see, depending on the value of delta, you know when the clock was started. When delta equal to 0, we started the clock when the object is at the origin. If the value of delta is pi by 2, then the object is at B when you start, and so on. So, this is the general equation. I want you to remember that. Y equal to a sine omega t plus delta is the equation for the displacement of an oscillation. Now, look at the oscillation one more time and see how you got a sine curve in this case. Of course, that's a sine curve because at t equal to 0, the object is at the equilibrium position. And this is a vertical oscillation. The oscillation is up and down. And what is the equation of a vertical oscillation? The equation of a vertical oscillation is y equal to a sine omega t plus delta. We use y because the vertical displacement is measured using y. What happens if the displacement, if the oscillation is horizontal? Have you seen example of a horizontal oscillation? Let's look at a vertical oscillation. See, now I want you to watch this carefully. I'm going to show you an animation. The same thing we discussed. This blue object is going to go around the circle, and the red object is, well, red is the projection. So what will the red do? Move up and down. And I will also trace out the path showing the variation of y. So watch that carefully when I animate it. There you are. You see? As the blue object goes round the circle, its projection simply moves up and down. And what does this tell you? This tells you how the value of y, the displacement, changes with time. Well, and what is the equation for that? Y equal to, in here, this is an animation that I borrowed from David Harrison. And in place of A I used for radius, David used R for radius. So this R stands for the radius, or in our case, the amplitude, the maximum displacement. Okay, let's go on to the next one. Now, how about if the displacement is horizontal? If the displacement is horizontal, we will simply replace that y by x. If the oscillation happens back and forth horizontally, the displacement will be measured in terms of x. Have you seen such an oscillation? Let me see if I can show you one. There you are. Now, in this case, if I pull this mass to the right and leave it, the mass is going to move back and forth. And it will give you the horizontal displacement, x equal to a sine omega t. Now watch this. That is an example of a horizontal oscillation. You can see that it's not got a lot of amplitude, but you can see how that actually happens. So an oscillation can be a vertical oscillation, the displacement V represented by Y. It can be a horizontal oscillation, the displacement we represent by A. Okay, let's move on. Let's now talk about position, velocity, and acceleration of an oscillation. Well, position is what is called a displacement. Well, if an object has a displacement, it has a velocity. Is that right? Tell me. You should be able to tell me this. Now, the position of this oscillating object is given by y equal to a sine omega t. Now, where does this object have the maximum velocity? From our discussions, where does this object have the maximum velocity? Well, the maximum velocity occurs when the object is in the equilibrium position. Is that right? And it has no velocity at either extremes. Now, how about acceleration? You see, when the mass is pulled down, now when I pull it down, the spring pulls it back. That means the load is now subjected to a net force. Now, anything subjected to a net force will accelerate, right? And where will the acceleration be maximum? The acceleration will be maximum where the stretch of the spring is maximum or the compression is maximum. So the acceleration is maximum at the two extreme positions, and the acceleration is zero at the equilibrium position. Well, I'm going to write the equations for position, velocity, and acceleration of oscillation. All right? I want you to take note of these equations. The position of an oscillation is something that we derive, y equal to a sine omega t plus delta. All right? And that's the graph of the position function. How does the velocity change? Now, since velocity is maximum where y equal to 0, is that right? Now, velocity is maximum at the equilibrium position where y equal to 0. And therefore, you can see velocity will be a cosine function. Now, this is the velocity function. Now, I cannot show you the derivation of it because it is a little calculus. In this course, we don't use calculus. So I'm simply going to give you that equation. Velocity of an oscillating object at any time is v of t is a omega cos omega t plus delta. It's a cosine function. So if I draw a graph, how will that graph look like? Where the position is 0, the velocity will be maximum. Where the position is maximum, the velocity will be 0. So you should expect a graph to go like that. It's a cosine graph. Look at that. That's the cosine graph. Where the position is 0, the velocity is maximum. Where the position is maximum, the velocity is 0. That's very interesting. How about acceleration? Where is the acceleration maximum? The acceleration is maximum at the two extremes. All right? The acceleration A of the oscillating object is given by, look at the equation, negative A omega squared sine omega t plus delta. Well, it's negative. That means, now if this is sine omega t plus delta, you can make it negative by simply inverting it. Now look at the graph of acceleration. That is the graph of acceleration equal to negative a omega squared sine omega t plus delta. So here you got a summary of how the position changes with time, the velocity changes with time, and the acceleration of an oscillating object change with time. All right, I want you to take note of these and keep track of these equations. Alright? So once again, where is the velocity maximum? Velocity is maximum where y equal to 0 at the equilibrium position. Now, where is the acceleration maximum? The acceleration will be maximum at the two extremes. Is that right? At the lower extreme and at the upper extreme, you have maximum values of the acceleration. But look at the acceleration equation. I want you to watch this carefully. A of t is negative a omega squared sine omega t plus delta. But look at the equation for y of t. Y of t is a sine omega t plus delta. Let's come over here. Let me go over and try and see if I can write it there. Now, tell me, what is this? A sine omega t plus delta. See, this quantity A sine omega t plus delta is y. And therefore, I can write A of t equal to, how will I write that? Alright. I can write A of t as omega squared negative omega squared y. And this is a very important equation. You see, acceleration of an oscillation is negative omega squared y. Can you interpret this equation? It tells me that acceleration is proportional to displacement. That means it's a very important statement. It tells me that the more is the displacement. If I pull the spring at a greater amount, the acceleration will be greater. And also it tells me that the direction of acceleration, the negative sign, the direction of acceleration is opposite to the direction of displacement. You see, if you look at this, the direction of displacement is downward when I pull it down. But the direction of acceleration is upward. Is that right? The direction of acceleration is opposite to the direction of displacement. There are two things that this equation tells you. The acceleration is directly proportional to the displacement, and the direction of acceleration is opposite to the direction of displacement. Those are the two information contained in this. And if you can put those two informations together, we would describe a very important type of oscillation. Well, so this suggests that acceleration of the oscillating object is directly proportional to its displacement, and it is directed opposite to it. Now, such an oscillation has a very good name in physics. It's called a simple harmonic motion, or abbreviated SHM. What is simple harmonic motion? A simple harmonic motion is a type of oscillation where the acceleration is proportional to the displacement and is directed in the opposite direction. That kind of an oscillation is called a simple harmonic motion. And from now on, for the next 2 or 3 classes, we'll be talking about simple harmonic motion. Let's now talk about period frequency of simple harmonic motion. Now, the period t of a simple harmonic motion is the time taken to complete one oscillation. What does that mean? The period is the time taken to complete one oscillation. All right, let me put this. All right, here we are. Now, if the object starts at the equilibrium position, the time taken to go up, back to the equilibrium, to go down to the lower extreme, and back to the equilibrium. That is what we call one complete oscillation. The time taken to do that is called the period of oscillation. So period t of a simple harmonic motion is the time taken to do one complete oscillation. All right? Okay. How about the frequency? What does the frequency mean? How frequently does it happen? Frequency is the number of oscillations per second. And we use the unit hertz for that. Hertz stands for per second. Okay. If you are thinking when you are listening to me, you should be able to give me a direct relation between period and frequency. Can you give me a relation between period and frequency? Period is the time taken for one complete oscillation. Frequency is the number of oscillations per second. For example, now suppose this object does 3 oscillations in 1 second. 3 oscillations in 1 second. Tell me, what is the time taken for one oscillation? If it does 3 oscillations in 1 second, the time taken for one oscillation is 1/3 of a second. If it does 5 oscillations in 1 second, the time taken to do one oscillation is 1/5 of a second. Can you give me a relation between period and frequency? You can see period T and frequency F are related such that one is the reciprocal of the other. If the frequency is 2, that is 2 hertz, 2 times a second, that means the period will be half of a second. So F equal to 1 over the period. That is an important relation. Frequency is 1 over the period. And do you remember we defined omega? What's omega? Omega is theta over t. Angle described divided by the time taken. Now tell me, when the angle is 2 pi radians, what does that mean, 2 pi radians? Now, what's it again? Equilibrium position. When it goes from equilibrium to upper extreme, the angle is pi by 2. From pi by 2 to pi to 3 pi by 2, 3 pi by 2 to 2 pi. Now the angle has changed by 2 pi. Angle has changed from 0 to 2 pi. And the object has completed one oscillation. That means during the time the angle changes by 2 pi, the time taken is 1 period. What that means is, what does that mean? It means when this theta is 2 pi, this t will be 1 period. So, can I therefore write that when theta equal to 2 pi, this t will be equal to 1 period. So when theta equal to 2 pi, the time t is the period. Therefore, omega equal to 2 pi divided by the period. A very important relation. Omega equal to 2 pi divided by the period. Alright, can you write this equation in terms of the frequency? What is omega expressed in terms of the frequency? All you need to do is, this can be written as 2 pi times 1 over the period. And 1 over the period is the frequency. And so, this can be written as 2 pi times the frequency. Is that right? So, omega equal to 2 pi divided by the period, which is the same as 2 pi times the frequency. Okay. What is the cause of acceleration of an oscillating object? I discussed that. Can you tell me, what is the cause of acceleration? Well, if the object is not pulled, it will not accelerate. So the cause of the acceleration is, when I pull it, the spring pulls you back. It is the force applied by the spring on the object which results in the acceleration. Is that right? So the cause of the acceleration is the force applied on the object by the spring, and we call it the restoring force. What's the restoring force? A force applied by the spring to restore the original position. Alright, so when you pull down the spring applies the force upward to restore its state. When the displacement increases, the restoring force F also increases, but in the opposite direction. Is that right? When you pull down the object more and more, the spring will pull you back with more and more force. And I can write this as a mathematical equation. Does it make sense? F equal to negative ky. Well, of course, that k is a constant. This tells you that the restoring force is proportional to the displacement. You pull the spring more, the restoring force will be greater. And the direction of that force will be opposite to the direction of displacement. Is that right? Well, that means I pull the object more, the spring will pull me back with more force. So the direction of the force is upward when I pull it down. When the spring compresses it, the direction of the force will be downward. Alright, so the direction of the restoring force is always opposite to the direction of displacement. F equal to negative ky, and this k is called the spring constant. There is different value for different springs. Alright, now it is this restoring force that produces the acceleration A, and therefore I can now write, you know that if m is the mass of the oscillation object, then that F will be equal to ma. Is that right? So if this F equal to ma, I can now write ma equal to negative ky. Is that right? I can write ma equal to negative ky. And so, now, do you remember we had, when you discussed about velocity and acceleration, we had said acceleration equal to negative omega squared y. Would you go back and have a look at that? So I'm going to replace this A by negative omega squared y. What happens to the equation? It will be m mass times acceleration becomes negative omega squared y equal to negative ky. And of course the negative on both sides will cancel. And that will give you omega squared. Is that right? Let me take you back in here. In this equation, the negative and the negative goes, y and y goes. And if you divide both sides by k, if you divide both sides by k, do you know, I want to solve for omega squared. Is that right? So divide both sides by m. Divide both sides by m, you get omega squared equal to k divided by m. Omega squared equal to k divided by m. That's an important equation again, don't forget. Omega squared equal to k divided by m. Alright, how many of you remember omega in terms of the period? Omega in terms of the period. Can you recall? Well, omega is 2 pi divided by t, the period. Is that right? Yes. Well, let's leave it. Now, if omega squared equal to k over n, then omega equal to square root of k over n. Okay, but omega equal to 2 pi divided by t. I hope you remember that one. Omega equal to 2 pi divided by t. So let's replace that omega by 2 pi over t, where t is the period. So what does our equation become? In place of omega, I have 2 pi divided by t, the period. So 2 pi divided by the period equal to square root of k over m. Can you solve this equation for t, the period? Well, now pause this presentation for a second or for a minute and try to solve this for t. What is t equal to? Well, solving for t gives me t equal to 2 pi square root of m over k. An important equation. What does that tell you? When you set an object into simple harmonic oscillation, you remember that word, simple harmonic oscillation. A simple harmonic oscillation has a period and frequency. What is the period? What is the period of this simple harmonic oscillation? The period of this simple harmonic oscillation is given by 2 pi times square root m over k, where m is this mass and k is the spring constant of the spring. Alright? Well, we will be using this very often as we move on, and I think we have done all the fundamental ideas of oscillations, and we will now try to apply in a couple of situations. What I'll do is the description of a simple pendulum. Well, let's see if we have time to do that. The oscillation of a simple pendulum is a good example of a simple harmonic motion. A pendulum consists of a hanging mass. Look at that. A hanging mass, now, where A represents the equilibrium position. Now, it will be something like this. Instead of making this oscillate up and down, if I pull this to one side and leave, you see, can you see the oscillation there? Well, that's not a very good example, but we will be working with simple pendulum there. Now, the length of the pendulum is L. When the bob is pulled to the position B, now, if you put the bob to position B and release it, the bob will move back and forth, just like a swing. You pull a swing back and leave it, it will execute oscillations. And that is what a simple pendulum is. Now, if M is the mass of the bob, then mg will be the weight acting vertically down. Now, the component of the weight mg cos theta, well, the tension T of the string will be acting that way, and that will be the angle theta. I suppose you can understand that. Is that right? The component of the weight mg cos theta will balance the tension. And the component mg sin theta is the one that's going to pull the object back to the equilibrium position, producing an acceleration A. So that this is the restoring force. You remember the case of a spring. The restoring force F equal to negative ky. And in this case, the restoring force is mg sin theta, and that's equal to negative ma. It produces that acceleration towards the equilibrium position. And that gives me A equal to negative g sin theta. Alright, suppose we say the displacement of the pendulum bob is x from A to B. Can you write sin theta from this triangle? Sin theta will be x over L, is that right? Opposite side divided by hypotenuse. I can write sin theta equal to x over L. So, I can come here and replace our sin theta by x over L. What will then A become? A equal to negative g sin theta. In place of sin theta, I wrote x over L. Well, do you remember the equation for the acceleration for a simple harmonic motion? Well, we have A equal to negative omega squared y. Is that right? So, let's replace our A by negative omega squared y and see how that's going to look. Now, comparing that, we get omega squared equal to G over L. Alright? And what is omega squared equal to? Omega is 2 pi divided by the period. So omega squared is 4 pi squared over t squared. Equal to G over L. Can you solve for t from that? Solving for t gives you t equal to 2 pi square root of L over G, where L is the length of the pendulum and G is the acceleration due to gravity. In fact, we will be doing a lab on this. I know I went through fairly quickly on this. The theory on how you arrive at it is not very important, but you must be familiar with that equation. The period of a simple pendulum, the oscillations of a simple pendulum is simple harmonic, and the period of that oscillation is 2 pi square root of L over G. Well, I think we are coming closer to the end of this lesson. There is a part that I would like to take up later, that is the energy of simple harmonic motion. That I will do in our next lesson along with solving some problems, alright? So I will see you for the next lesson to solve problems using the concepts we developed today. Alright, I will see you for the